Okay, great. So let's just remember where we are. So we have this notion of differential privacy. We saw some properties of this notion. We saw a few algorithms that preserve it both in the local model where people add their own noise and in the centralized model where we added noise to some numeric statistics. And we saw that sometimes it pays to be a little bit more clever than just adding noise to statistics separately. So we thought a little bit about histogram queries and this report noisy max algorithm last time. And this time I want to give you one more basic tool for privacy that moves us to a very different set of problems that we can deal with. So moves us outside the space of numeric queries. And then I want to apply, although probably with very little analysis to back it up given the limited time, I'm going to apply this tool to help you see that it is possible actually with sort of sophisticated noise coordination to potentially answer many, many more queries than we've seen so far. It's hard to sort of scope the introduction to differential privacy to so few lectures, but I think by the end of today, you at least have not quite all of the sort of main Lego building blocks, but you have most of them. You have some sense of this idea that you can sort of put them together into interesting, sort of more complex algorithms. I won't get to survey it for you in this course, but you should know that there is a very large and rich literature that goes around looking at interesting things that people like to do on data and trying to figure out how to do them subject to guarantees of differential privacy. So basically sort of taking these building blocks and assembling them in interesting ways in order to give guarantees of differential privacy for lots of statistical, machine learning, lots of interesting tasks. And just about that, I'll just say that sort of intuitively, there are a number of different points in a computation that you can think about introducing the noise that is necessary for differential privacy. And you see all of them happening in the literature in various ways. So it's not just sort of one formula that you apply to take a non-differentially private algorithm and turn it into a differentially private one, but there is some sort of creativity in the process and figuring out the impact of adding the perturbations at various points in the computation. So at a high level, you can think about, for example, if you're doing a machine learning task, you can think about perturbing the data. You can think about perturbing the learning process. You can think about perturbing the objective that you're optimizing. And all of these actually can and have been used to achieve differential privacy. And it's not immediately comparable what the types of guarantees you'll get are. So there's real interesting sort of work and thinking to be done in figuring out how to make differential privacy fit, and of course, in adapting it to sort of more and more settings. Okay, so for today, the new tool that I want to give you is a tool that gets known as the Exponential Mechanism. And the idea here is, what if we want to be able to guarantee differential privacy for computations where just adding noise doesn't make sense? So far, we basically figured out the right answer and added noise, or just added noise to the input. But what if you're doing a computation that has non-numeric outputs, or you're doing a computation where you have numeric outputs, but we're adding noise to them could potentially destroy the quality of the outcome? So, why would that be? A little bit of noise should never hurt. But you can think that actually a lot of situations where you want to do a computation, the quality of that result is sometimes brittle. If you think about an auction setting, which was the setting that was the motivation where this tool was first invented, if I get exactly the right price for an auction, then potentially lots of people are willing to buy at that price. But if I'm unlucky and nobody's willing to buy at a price that's $10 higher, then I could potentially add a little noise to my price and go from selling my goods to lots and lots of people to selling it to nobody. So you could potentially, think about systems and sort of even more realistic and complex systems where you can have some brittleness to noise, even if the output is numeric. But then also you can think about wanting to preserve privacy for outputs that are not numeric. Maybe I want to come up with a policy decision about which geographic location to use for a treatment center for disease. Maybe I want to, and how do you add noise to that? I mean, you could sort of wiggle around the locations, but maybe that's not the thing that makes sense. Maybe I want to use differential privacy to produce synthetic data. You know, what does it mean? What does it mean to add noise there? So we want to develop a sort of richer vocabulary for thinking about how we can preserve differential privacy. So suppose we have, and this is going to be the basis for how we pick what to do with these algorithms. Suppose we have access to some utility function that, given an input database, tells us how good a potential output is. And that sounds pretty abstract. Let me write that down for a second, but let's think about what that would mean. So that it scores outcomes. So we assume we have something that takes databases and takes, you know, a potential outcome and say return some real. Sorry, I'm copying the book's notation. I hate the R's and R's with just different fonts, but hopefully my fonts look slightly different to you. So the idea is that suppose that you have some way of deciding, given a database, what constitutes a good output for your algorithm. This is kind of something you're going to need if you're going to be able to optimize. So this is not a very demanding assumption. The idea behind the exponential mechanism is to think about your space of possible outputs for your algorithm. And again, it could be numeric, but it could be something else. So you just have some world of possible outputs. And given the database that you have at hand, each of them has some quality. You know, this would be a particularly good output. I guess let's do bigger scores or higher. This one would be a particularly good output. You know, this one's slightly less good. This one's, you know, quite terrible. This one's somewhere in between, and so on and so forth. So each one has some inherent quality. And what we'd like to do is we'd like to output something that's of pretty good quality. But of course, we need to preserve privacy, so we can't just output the best outcome, but we'd like to at least bias our choice of the outcome towards the ones that are better. So what we want to do is we want to define a distribution over outcomes that's concentrated on the outcomes, but that is somewhat stable, so that it's not, that distribution is not going to change very much from the distribution that would have been induced by a neighboring database. So this is the, you know, quality, these are the qualities that were induced by one database. But if we look at, you know, a neighboring database, maybe the qualities would have been slightly different. So maybe this one actually didn't look as good, and, you know, something like that. And so we would like these, you know, slightly different scores on the outcomes to induce similar distributions over the outcome that we pick. So it seems now, given this sort of idea of what we're trying to achieve, perhaps not so surprising that a useful thing for us to think about is going to be the sensitivity of this scoring function with respect to the database argument. Sorry. So what do I mean by this? I mean, this is the sensitivity. I mean, how much over all of the outcomes that you might consider and over any pair of neighboring databases can this sensitivity function change? I mean, sorry, this quality function, this utility function change. We call it a scoring function, we call it a quality. So how much can moving between databases change qualities for any outcome? Okay. And intuitively, this is the thing that is going to be sort of the thing we have to fight against. Because if changing from one database to a neighboring database could change the score of one of these outcomes substantially, then it's going to be harder for us to ensure that we're always, concentrating our probability mass on good outcomes. If the scores are very similar under neighboring databases, then it's going to be easy to maintain sort of stable distributions that are good. And now with all of this in mind, we can finally define the exponential mechanism, which is actually a really simple approach. So given a database and given one of these scoring functions and a space of outcomes, what it does is selects and outputs an outcome, so one of these potential outcomes, with probability that's proportional to the following function. Exp, epsilon, the quality of that candidate given the input database. And this 2 that you'll see where it comes from, don't worry about right now, times sensitivity of the scoring function. So what is it saying? This is saying literally, bias your choice of the outcomes towards the ones that are good, but when you want to guarantee good privacy, okay, what does that do to the epsilon? When you want to guarantee good privacy, that means small epsilons, right? When you want to guarantee good privacy, you can do less biasing. That's sort of going the opposite direction. And when the sensitivity is big, you also, you're gonna have, I mean, that's fighting against, in some sense, your privacy guarantee. Make sense? Okay. So intuitively, why is this doing what we want it to? Well, intuitively, what's going on is it is doing this biasing towards the good outcomes. Is this going to give us a good result? Well, that depends. And depending on how we're doing on time, I may or may not prove with you the formal types of accuracy guarantees that you can get here, but let's already sort of think ahead to what those could potentially look like. You can already see that the quality that you're going to be able to guarantee for this is going to depend a little bit on the structure of your problem space. I mean, even sort of fixing this sensitivity of the scoring function, if I have a problem where all the outcomes are really good, it's not going to be hard to guarantee good accuracy. But if I have a problem where some of the outcomes are good, but a lot of them are really bad, then it's going to be harder to ensure that I've concentrated probability mass on the good ones intuitively. Okay. So let's start first, though, with the proof of privacy. And you guys are experts now at how to do a proof of differential privacy. So let's get started. So the theorem says the exponential mechanism preserves epsilon differential privacy. Okay. And as usual, let's make our lives easy by thinking about sort of a discrete, finite space of outcomes. And then we're going to define, just so that I can write fewer symbols, because you're about to see this proof involves writing a lot of symbols, define just delta to be my delta u. So I just have to write fewer u's. And what do I have to do? I have to consider a pair of neighboring databases. And consider some R in the outcome space. And now what do I want to look at? Well, I want to look at the ratio of the probability that the mechanism returns R given X versus the probability that the mechanism returns R given Y. This is already starting to feel like very routine, very rote, which I hope is good. So the probability that the exponential mechanism returns R on X versus the probability that the mechanism returns R on Y. Well, what is that? Let's sort of plug it in literally. So we know what the numerator of the probabilities is, but remember this was proportional to, so we're gonna have to get a denominator on those probabilities too in a moment. All right, so this is x of what? Epsilon u of xr over 2 delta. Please catch me if I make a mistake. So now I need to do a denominator here. So this is proportional to, so I just need to sum up the probability mass on each of the outcomes. So let's do that. Epsilon u xr prime over 2 delta. Okay, that was the top. Now we got to get ourselves the bottom. You see why I would want it to cut back on writing. Epsilon u of yr over 2 delta. Epsilon u yr prime over 2 delta. That all makes sense so far? Okay. Now what should I do? Well, one thing I can do is I can try to reorganize this to make these terms a little bit easier to sort of make sense of and deal with. So let me do that and see if some ideas start to emerge here. So first let me, take this one and put them together. So that's xr over 2 delta over x of epsilon u yr over 2 delta. Maybe you're already even getting an idea about what we can do there. And here we got this, mess with the sums. So x epsilon u y r prime over 2 delta, because that was the denominator of the denominator. And now we have the denominator of the numerator. Epsilon u of x r prime divided by 2 delta. Okay. So now what? What can I say about, this term here? Well, maybe I can keep rewriting it in sort of the natural way and see if something familiar starts to show up. So this is equal to x of what? I've got an epsilon, and I've got a u of xr minus a u of yr. Well, that's looking promising. And a 2 delta. Why do I say that's looking promising? What can I say about this?
This look like the sensitivity.
Yeah, exactly. That's the sensitivity. Yeah, so that's bounded by my delta. That's good news, right? Okay, so now let's try to make some sense of this other big mess that we've got going on here. So what do I know here? Well, I can say, because of that sensitivity bound, I can replace this. I should have done that in a different color. You couldn't see that at all. I should replace this term if I wanted to. I could upper bound that with the term that substituted an x and added a delta there. So how about I try that? So this is then less than or equal to here, for this piece. I've got the sum over r prime and r, x of epsilon times u of x r prime plus delta divided by 2 delta. All of that, r prime and r, x epsilon u x r prime over 2 delta. Okay, so let's first make sense of that first term. So what have I got here? I've got an exp of an epsilon times delta over 2 delta. So I could just call that an epsilon over 2, right? What have I got over there on the right-hand side? What can I do with that?
You can write it as a product.
Yeah, let me pull something out there on the top. I'm trying to make that make more sense. So I've got a sum here of r prime and r of x epsilon u x r prime over 2 delta times an exp of, what have I got here, an epsilon times a delta divided by a 2 delta. Is that right? Does that look pretty good? And then same mess going on in the bottom as I've been carrying around all along. So that's an epsilon x r prime over 2 delta. But that's starting to kind of look promising, no? Yeah, what can I do there?
You can factor the exp epsilon delta over 2 delta.
Yeah, let me pull that out. What happens when I pull that out?
The messy terms they cancel each other.
Hooray for messy terms canceling. Exactly. Yeah, so that all cancels out. And yeah, sorry, my messy handwriting really mixed the messy terms. And so now we've got an exp of epsilon over 2 times an exp of, nice, epsilon over 2 equals an exp of epsilon. Are we done? Was there anything special about the x versus the y? Did I know which one was bigger? Anything special? Nope, it was symmetric. We're good. Okay. So that's the proof that the exponential mechanism preserves differential privacy. And given the time, I think I'm not going to pull us through the proof of accuracy, which I know is not very satisfying, but it leverages exactly the intuition that I was talking about before, that the level of accuracy that you're going to be able to get is going to depend, in some sense, on how many good outcomes there are versus on how many outcomes there are in total. And that's going to affect what type of guarantee that you can get. And sort of the flavor of the accuracy theorems that you can prove are things that say that the probability that you return an outcome that's substantially worse than the optimal outcome is small, but the substantially worse than term is going to depend on your epsilon, it's going to depend on your sensitivity, and it's going to depend on how many good outcomes you have versus how many bad outcomes you have. The good news is that ratio between bad versus good outcomes is going to show up inside a log. And so you're still going to be able to run this mechanism and get interesting results, even when you have sort of exponentially many possible outcomes in the natural parameters. So this remains a pretty powerful tool, despite the fact that you have the dependence. But sort of knowing intuitively that that dependence is there helps sort of guide your intuition for when this is going to be something you can apply. Okay, questions?
Just a quick question. So this proof, like it kind of relies on the fact that R is discrete in some sense. Would it be hard to adapt the mechanism to like a continuous outcome space, and would there be any tricky parts in that adaptation?
That is a good question. I have not thought about that carefully enough. I think it is entirely possible, but off the top of my head, I want to be careful. I have to think carefully to tell you exactly what is going to happen to you when you move out of the discrete world. I don't think you're going to get into any trouble, but it is subtle. So but let me not answer that now and try to follow up later once I can get a chance to think about it offline.
Perfect. Thanks.
Yeah, thanks. It's a good question. Yeah, and you're totally right to notice that sort of this was a very discrete approach. Yeah. Other questions? Okay.
Just along the same line, just spitballing. would the sum just become integrals and would everything still just work out nicely?
That's what I wanted to say, but then I thought I shouldn't say that without thinking for 3 more minutes. So I think so, yes. But I want to think about it before I say something like that. Just made me nervous to say yes. So yeah. Okay. Let's continue on. Okay. So the place I want to go next with this, and so there's lots of really cool things you can do with the exponential mechanism. The first thing I ever did with the exponential mechanism was working with Avram Blum and Aaron Roth to use the exponential mechanism actually to help us produce synthetic data. So what do I mean by that? I'm going to talk just at a very high level about what we do there, and then I'm actually going to present a different mechanism that's, I think, offers maybe some more intuition for producing synthetic data. But what's the synthetic data problem? So one thing you can do if you have a database and you want to, enable people to do interesting things with it is you can say, come to me with your computations and I will run them with guarantees of differential privacy and I will give you answers. I will curate the database. And then I will keep track of all of the privacy losses and I will maintain the privacy budget. I'll stop answering questions at some point, something like that. But another really desirable thing that you might want to do with a database of sensitive information is publish a version of it that you can then just hand to researchers. And then you can go home and sleep. You don't have to be bothered with their questions and they can go off and do their science. That's a very natural model that you might be interested in for a variety of reasons. What's the problem with that? Well, one can show sort of from the intuition that you build thinking about differential privacy and sort of the negative side of differential privacy, sort of the impossibility of resulting reconstruction attacks, is that it's not possible to produce this sort of synthetic data that's going to be useful for all queries that one could ever imagine in the future. That kind of makes sense. So if you want to produce synthetic data, you have to anticipate in advance what queries people might want to issue on the database. You can produce synthetic data that will be good for all of those queries. But then you tell people, these are the queries that you can go and run on this data. Feel free to do as many of them as you want. Anything else, all bets are off. And the cool thing about doing this process, this production of synthetic data with a differential privacy guarantee, is you can produce the synthetic data, announce what it's useful for, and then go home and go to sleep. And people can run as many computations as they want to on that synthetic data, as many times as they want to, and in as many places in the world as they want to, and they can think about them as hard as they want to, and they won't break your privacy guarantee. And that's because of that beautiful post-processing theorem that we saw 2 days ago. If we can prove that the process that produces synthetic data enjoyed a particular level of differential privacy, then subsequently anybody can do anything they want to with that synthetic data. And that's really, really appealing. So the question is this synthetic data thing possible? And if so, can you do it for any sort of meaningfully large set of queries? So can you produce synthetic data that's simultaneously good for not just one query or 10 queries, but sort of the whole vocabulary of queries or a large vocabulary of queries that researchers might be interested in? And yeah, go ahead.
So just one question. I mean, okay, so you're gonna certify that nobody can break the privacy of the released synthetic data, but eventually they're gonna break the accuracy of that synthetic data, or unless you prescribe what kind of queries they're allowed to make, right?
Yeah. So what you have to do is you have to tell them this synthetic data is valid for the following set of queries. If they can issue those queries as many times and all of them as much as they want to in the data set, but if they want to issue other queries, you don't give them an accuracy guarantee. But the cool thing is it's accuracy that breaks and not privacy. So if somebody comes up with a sneaky query, the worst thing they can do is get the wrong answer. They don't break the privacy. And that's pretty nice. But yeah, that's a really important point. If you didn't anticipate the queries that scientists are going to want to run, or the scientists misunderstood and thought they could run some other queries, all bets are off. They could get garbage. they could get lucky. I mean, it could be that their queries were sort of in some sense accidentally preserved by the process. You know, no guarantees. Yeah, that's an important point. So the first points that I encountered sort of using the exponential mechanism was actually in using it to show that it is possible to produce synthetic data. And the idea behind that algorithm in proof is just the following realization, that it turns out that if you have sort of a large set of queries that you might be interested in on a data set, that there exists a small data set whose size grows with the logarithm of the size of the class of queries that gives the right answers to all of the queries. You also have to have some dependence on what you mean by right, you know, some accuracy parameter, but let's not worry about that for the moment. So, and you can state, I mean, if you've encountered, you know, learning theory, VC dimension, you can state similar types of statements if you have a bound on the VC dimension of the class of queries, but let's ignore that for now. Just think about it, if you have a set of queries that you're interested in, it turns out that there is in some sense a compact representation of the answers to all of those queries. You don't need too many data points in order to, you know, create a database that gets sort of the right answers to all of them. And that ends up being useful because you can then say, well, let's use the exponential mechanism to sample a synthetic database of small size. And it turns out that that ends up being enough to show that there exists, you know, a mechanism. It's not a computationally efficient mechanism, but there exists a way to produce synthetic data that's differentially private. So that was just too high level to really totally believe, but that gives you some intuition for the mechanism that shows up in the book under the name of small db. So if you go in and look at that, that's sort of hopefully you have a little bit of intuition for what's going on there. What I actually want to show you today, though, is a different algorithm for producing synthetic data subject to differential privacy, because I think that one contains some sort of nice intuition. So the algorithm that I want to show you is the multiplicative weights exponential mechanism. Or MWEM algorithm. So that small db algorithm that I just alluded to, the intuition is in some sense, somewhere out there, there's a small database that answers all the queries pretty well. And in a differentially private fashion, we can use the exponential mechanism to select, therefore, a pretty good small database, you know, with reasonably high probability. The intuition here is a little bit different. The algorithm that we have here is that we want to progressively learn good synthetic data. So the idea here is that we're going to start with really bad synthetic data, and we're going to progressively make it better and better, meaning we're going to make it so that it does a better and better job of answering the queries of interest, similarly to how those are answered on the true underlying data set. And so the idea here is you've got some, so I'm going to sort of sketch the algorithm here. Oh, somebody's posting questions and I'm not watching. Is somebody else watching questions?
There's one question in the chat.
Yeah, okay. So do you keep losing privacy as you release new synthetic databases created from the same original one? Yeah, so if you wanted to create multiple synthetic data releases, each of those would be a differentially private algorithm, a run of a differentially private algorithm, and so you would pay in privacy for each time you created synthetic data. So for example, I created synthetic data, and then, you know, a few months later, I realized, oops, I didn't make that synthetic data accurate for, you know, these queries that people really care about. Let me make some new synthetic data. You'd have to pay again to create new synthetic data. Yeah. And you know the queries that each database can answer. Yes. So you can make public the information. These are the queries that this synthetic data supports, and these are the queries that I give you no guarantee on. So you can sort of explicitly or implicitly just give people a list of the queries that it's good for. Yeah. That's one of the sort of themes of differential privacy, actually, in some sense, is that you're not getting privacy by secrecy. It's not secret what the accuracy parameters or privacy parameters are. It's not secret what questions you can answer well and which ones you can't. You're not hiding sort of behind secrecy. The only thing that's secret is the randomness of the algorithm. So you can't show somebody the randomness you used in your noise, but other than that, there are no secrets here. Yeah, somebody else was saying something.
Yeah, I just had a quick question about the small dB algorithm that you mentioned.
Yeah.
Sort of getting a smaller version of the database with the log parameters sort of sounds like a sort of application of JL in terms of projection, like a Johnson-Strauss projection to get to a smaller dimensional space. Is that at all related?
So it's not directly related, but it's a really good intuition, and there is actually nice work on the relationship between sort of JL and differential privacy. In my mind, at least, maybe there is some way to make a more formal connection. What's going on is, okay, one way you can prove that there exists a good small database is you can just prove that randomly subsampling gives you a good small database. And so in my mind, what's going on is you just need the existence of a good small database. And actually the proof only relies on the existence of one good small database. And then just because the databases are small, there aren't that many of them. And if you recall, intuitively, the exponential mechanism accuracy statement is going to just rely on there not being too many sort of total databases or bad databases. So the database that you actually output, it's a little hard for me to think about what that looks like and what its relationship is to sort of a projection, but it's an interesting question whether there's something maybe more concrete to do to connect them. Thanks. Okay, so different algorithm. Now we're going to try to learn synthetic data. So what's the idea here is we're given a database. And here, sorry, we're copying notation. Again, that doesn't, always use the best notation. Sorry, it's my fault this time. And you get some set of queries. And we're going to have some parameter for the number of rounds that the algorithm's going to run. Let's not worry too much about that, but it's going to show up. So, try to ignore that for the moment. We can talk about it in a second. Okay, so now what am I going to do? I'm going to start with candidate synthetic data. But it's going to be terrible synthetic data. I'm going to start with the uniform distribution over all possible database entries. Okay, so what does that mean? So it doesn't exactly look like a database. So forgive me for the next 5 minutes. I'm going to talk about distributions over the space of possible data elements as if they were databases. Okay, you can imagine turning them into databases by rounding or sampling or something later on. But for now, just let me talk about distributions over the space of possible database entries. Okay. And now what I want to do is, that's probably a pretty bad synthetic database. Why? Because it has nothing to do with the input data. It probably doesn't do anything to answer the queries correctly. So I want to incrementally improve it. How am I going to do that? Well, I'm going to do a little cycle over and over again to make little improving steps. And what does it look like? On each of these steps, the first thing I'm going to do is I'm going to find a sort of way that I need to improve. I'm going to find a bad query with the exponential mechanism. So what do? I sample some query from the space of queries that we're interested in using the exponential mechanism with a parameter of epsilon over 2t, and a quality score that basically says how badly does that query do compared with the true data, sort of how badly does my candidate data do on that query compared with the true database. Okay. So that's a way of getting a bad query in a differentially private way. Now that I have that bad query, a query on which my candidate database is doing badly, now I want to figure out how to improve my candidate data with respect to that query. So I'm going to first measure that query with the Laplace mechanism. So I measured the true value of that query on the true data, and then I add Laplace noise. It's so fun to use the tools you've already built. And now I'm going to use that information to improve my candidate output data. So I'm going to update using the multiplicative weights idea. And if you may have encountered multiplicative weights updates somewhere in your life, if not, I'll just explain the intuition in just a moment. Just let me write it, and then I'll make it make sense. So basically, I take the previous distribution, and sorry, -1. So basically, and then I'm going to rescale the elements of my data distribution. And you could think of this as telling me, in some sense, like, you know, whether to scale up or down. And this is, you know, how badly we did. But intuitively, what's going on is, okay, here's a query you're doing poorly on. Go through all your database elements, and you're going to bump them up if bumping them up makes you do more well on this query, and you're going to bump them down in terms of how much probability mass they get if bumping them down makes you do more well on this query. Does that make sense? So I have a database, you know, I have a data distribution. Here's a query it's not answering well. Okay, so we need some of those data points to be more likely and some of those data points to be less likely. And I just bump up and bump down accordingly. And now I repeat. So now I have a slightly better data distribution as my candidate output data set. And I say, exponential mechanism, give me a query on which I'm doing poorly. You get that query back and you say, Laplace mechanism, please tell me approximately the correct answer for this query. And then you use that to say, okay, multiplicative weights update, let's improve my distribution by bumping up the points that need to be bumped up and bumping down the points that need to be bumped down. Repeat. And then, because this is how, you know, most analyses of the multiplicative weights work, you output actually the average rather than the final one, but let's ignore that now. Okay. So we don't have the time to actually analyze this in any sense, but we actually have time to do the privacy analysis. What's the privacy analysis of this algorithm? Well, you can use a composition theorem because you did a bunch of differentially private computations. And you're just going to use that naive composition theorem that we proved where you can add up your epsilons. Where do we do something that's differentially private that we need to account for? Well, we do it here and we do it here. how much do we pay? You know, that's how much we pay here, and that's how much we pay here. How many times do we do it? T times. What's T times epsilon over 2T plus epsilon over 2T? It's epsilon. That was the privacy analysis. Done. So that's the power of having a composition theorem and having building blocks, is you just developed this complicated algorithm. Proving accuracy is more work, which is why we don't have time to do it. The privacy proof was super easy. And you can even modify this algorithm to do cooler things, to sort of get the queries on the fly rather than having them in its pocket right at the beginning. And just, it can check whether or not this is a query it already knows how to answer, or it can sort of, if it doesn't know how to answer it, it can do an update on that query. We don't have all the technology to do that update. We're missing like one building block for that, but we're really close to it. So that's kind of cool. And the really cool thing in all of this that I haven't really gotten, you deep enough into it to see, is that with this algorithm and with the previous one that I sort of alluded to, we're all of a sudden able to answer not just sort of quadratically many queries in the relevant parameters that we've been running around with, but actually we're able to answer exponentially many queries. And if that just sounds sort of impossible, why? Why is that possible? What's going on here in some sense is, instead of adding Laplace noise to each query separately, we're adding noise that correlates and coordinates across the queries. We're developing these techniques that what they're doing for us is basically they're discovering how the queries that we get are related to one another, and how we can coordinate the noise that we add in some sense across the queries to be able to handle many, many more queries. And that's sort of the cool secret that I wanted to get to in this lecture, was this realization that if you develop mechanisms that coordinate their noise across the queries in some sophisticated way, that can allow you potentially to answer many, many more queries than just literally, adding Laplace noise on each go. And that's sort of a general principle to think about. Is, one thing you can do when you're trying to do something in a differentially private way is to try to break it down into, sort of the component queries and answer each of them separately. But sometimes there's a real benefit to be gained in thinking a little bit more holistically about how the queries relate to each other. Questions?
So this whole update mechanism depends on the, in some way it will depend on the number of queries and also the choice of this T, but it looks kind of expensive to each step.
Yeah, so okay, good. So let's talk about this a little bit more. So the T ends up being something that is in some sense trading off for you. As you run more and more rounds of this, you are obviously improving, but there's some cost because you're making less improvement on each step because you had to do this, dividing out by the T here. So there's, in some sense, that you can optimize the T to get sort of the best overall improvement. So the T is just something that you work out what the right value is. It ends up, being in practice not a very large T. Computationally, yeah. This is as written a pretty horrendous thing to think about doing. I've asked you to carry around a vector that contains a probability for each of the possible database elements, and they sort of update this. But you don't literally need to implement it that way. So if you want to make this a little bit more practical, although this is not the most practical algorithm there are more practical ways to create synthetic data than this. But if you want to make this, actually runnable on real data, you can. And you can do it in the following way. You realize that actually you don't need to keep a literal representation of that candidate output database at all times. All you need to do is you need to keep track of the updates. And if you just keep track of the updates, then you can use those to recreate sort of a representation of the data. The other thing to realize is this is a very sort of parallelizable algorithm, which is potentially beneficial. But you were totally right to be sort of skeptical about practicality on large scale. This is, there are better ways to produce synthetic data, and producing synthetic data is a computationally heavy thing to be doing. But the cool thing to maybe point out is just that you are able, with algorithms like this, to get accuracy guarantees that scale in sort of square root of the log of the size of the class of queries. So you were answering exponentially many queries rather than sort of the quadratic that we could have gotten just from our advanced composition on using just direct noise addition. So yeah, unfortunately, we're sort of like stopping in this moment where it feels like, oh, we're so close to so many things. But hopefully at least this gives you a taste of, sort of where this is going, and there are fun things to do here. Really, I think sort of whatever your passion is in computer science, whether you're sort of more geometrically inclined or sort of more of a practical databases person, whether, I don't know, you really like sort of, basically sort of wherever you want to go. If you're more of a cryptographer, there are beautiful connections to many, many subdisciplines that you see in differential privacy. Lots of really nice work that's been done over the past couple of decades. If any of you are interested now or at any point in sort of finding your way into the literature, feel free to send me an email and sort of say, hey, this is what I'm interested in. Do you know of literature that makes this connection or that has this flavor? I'm happy. I don't have a perfect index in my head, but I'm happy to do my best to help you find your way to the right entry point for you guys into the literature. Yeah, any other questions?